Hi everyone, this is Jeet Damani from TE Electronics. So in this experiment we are going to design inverting and non-inverting comparator and see some of its applications. So now moving on to the first inverting comparator. Then the comparator is op-amp is used in the open loop configuration, and the sinusoidal input signal is applied to the inverting terminal of the op-amp, and the reference voltage is applied to the non-inverting terminal. And when Vin is greater than Vref, then the output will be minus Vset, and when Vin is less than Vref, then output will be plus Vset. So now first we will see for input frequency of 50 Hz, we will simulate it. So as you can see, when the input voltage is greater than Vref, the output is minus Vset, and then input voltage is less than Vref, then the output is plus Vset. Now we will increase the frequency to say 5 kHz. So as you can see, there is a distortion in the output signal. This delay is because of the slew rate of the op-amp. So for this, as the frequency increases, the open loop comparator, there is a distortion in the output signal. Now we will move on to the non-inverting comparator. So in the non-inverting comparator, the input signal is applied to the sinusoidal input is applied to the non-inverting terminal of the op-amp, and the reference signal is applied to the inverting terminal of the op-amp. And when Vin is greater than Vref, then the output will be plus Vset, and when Vin is less than Vref, then the output will be minus Vset. So now we'll simulate this. So as you can see, when Vin is greater than Vref, the output is plus Vset. When Vin is less than Vref, the output is minus Vset. Now we'll increase the frequency of the sinusoidal. We'll change it to 5 kHz. Now we'll simulate it. So as you can see, there is a distortion in the output signal because of the increase in the frequency. The open loop comparator output gets distorted. So we need to use a higher slew rate op-amp for this. So we have seen for the higher frequencies there is distortion. As the frequency increases, the output voltage gets distorted. Similarly for the non-inverting comparator, as we have seen, for the higher frequencies the output is distorted. Now we will see the zero crossing detector. Zero crossing, here we have designed a non-inverting zero crossing detector. So here similarly it is same as the non-inverting comparator with a Vref of 0 volts. So the input signal is applied, the sinusoidal input is applied to the non-inverting terminal, and the Vref, that is 0 volts, is given to the inverting terminal of the op-amp. So when Vin is greater than 0 volts, the output will be plus Vset, and when Vin is greater than 0 volts, the output is plus Vset, and Vin is less than 0 volts, the output is minus Vset. Next, the application of the comparator is time marker circuit. Here in the time marker, the first stage is a zero crossing detector, so the output will be a square wave, and then we have a differentiator circuit which will differentiate the square wave and will get the spike signal, as you can see over here, positive and negative spikes, and then the diode will filter the negative spikes and will get only the positive spikes at the output. Now the next is a sample and hold circuit. The sample and hold circuit samples analog input signal and then holds it until it is sampled again. So now the input signal is when the here is the control voltage, when the control voltage is high, the capacitor starts charging and it follows the input signal, and when the control voltage is 0 volts, then this MOSFET is turned off and the capacitor holds its value, holds its charge, and this op-amp is used in the buffer configuration. So as you can see, the input signal is sampled and then the capacitor holds a charge for this time. Thank you.